we were we were here actually. We were creating, building up our recurrent neural network. It is also a sequential design. As you can remember, there was a line of chunk of networks. So it's a sequential. This is the main architecture of the recurrent neural network. It is similar like artificial neural network, the same one. And now in the second coding line, now we will use layers. We will create our neurons, okay? What kind of neurons, how they communicate with each other. So, and normally, a normal artificial neural network, if you remember, we are just using dense layer, and we are adding different dense layer, hidden layer. But for this kind, we will not only use dense layer, as I shown from previous figures. There is a complexity in this kind of neural network. So we need to here we need to add different layers for this one. Yes, we are here. Yes, let's add. I think it's work. LSTM, we have added LSTM, and we will add this. This is the latest one. Let's copy this one, and we will just change the name of the layer. Okay. Instead of LSTM, we will just use bidirectional. Directional. I will explain. Bidirectional. Yes, that's it. After importing the sequential model, the first thing we have to create an object or an instance of this model. Okay, so I will simply say recurrent neural network shortcoming RNN as equal sequential. Okay, now I will run this one. And I want to show you from the other one step by step what we are creating by coding. Let's find my work. That's this one. Now, yes. Yes, we are now creating this sequence of lines, okay? Sequence of networks. This is a sequential model. This is the first step. And now we have commanded the algorithm that we are creating a sequential model. We have run this one, okay? And next step is we will add our layers, okay? For artificial neural network, we are just adding dense layers, but for this kind of recurrent neural networks, we are adding different layers. For example, the first one should be always embedding. Embedding, yes, and this function, as you can remember, there are 10,000 words. This represents number of words. This is hidden, embedded inside the previously created words. So we want 16 of them. You can play around these numbers, but not this one, because for this number we are using 10,000 words. So we are creating 10,000 chunk of layers, okay? 10,000 each of them, 10,000. We are creating 10,000 each of them now. And after that, let's run this code. Now we will add bidirectional. I'm sorry, first add. Now after that, bidirectional Yes, bidirectional. Inside this one, we will write LSTM. This is the previously created very good version for creating long memory for recurrent neural networks. We're creating 20 of them. Return, I will explain all of them. Return sequences, true. As you remember, we have created sequences from words to the numbers, and we are now commanding that, yes, do this one, true. And let's run this one. Yes. After now we are dealing with these inner parts of each single chunk of network. Okay. By sequential, we have commanded we are sequential lines of networks, and after that, this is the main model. After that, now we are creating layers. We say that we want 10,000 separated networks, 10,000, which which of every one of them represent one word. Okay, and every this chunk of network, now we are creating how this recurrent neural network deal with the problem, right? As I said previously, this LSTM model is very good for long-term memory. So because it enables us to forgetting a word, creating a new one, or for example, creating a gender or something like that. So for this line of code, bidirectional means it will go, uh, this direction. It will forget, or it will add this new word to this line of information follow, or if it does find it, you can also turn this one bidirectional. It will turn to the previous layer also bidirectional. It will work multi-directional, we can say it. Not only working one direction, also coming back according to the result. And we are creating 20 of them. And the third one, also we are creating another one. Let's, after running this one, for this LSTM, we don't need return sequences. This will work with the original data. Say yes. And now we have created these the content of this every single chunk of network. It will work in bidirectional, and it will use the LSTM model. Now after that, we will compile what kind of function inside of each of these layers will be, and we will use another function after that, but our model has not ready. We have already created that one. Yes. No, we click two times, and that's not good. Just we are created one time, so it has already transformed, and now we are adding the dance layer. Then that add dance layer. As you can remember, we have just 6 outputs from the TVs. According to the output of this every recurrent neural chunk of neural networks, we will predict 6 outputs. One of them is sadness, the 6 emoji, sadness, love, or joy, something like that. Now we are creating our normal artificial neural network I'm trying to find you this. Yes, this image. Now we are creating this dense layer, which means we are now creating normal artificial neural network. Okay, and uh, the output of normal this neural network will be one of them. There are 6 units inside this one. It will predict sadness, love, or something like that. We have 6 labels, so we are creating 6 units for this dense layer. And but for dense layer, we have to also we have to use activation function. Now we are making what kind of operation this network, this dense layer will work. Softmax, one of the activation functions for this kind of problem with when we deal with the words. Yes, and now we will compile that compile. This means we are what kind of operation we will use every separate layer inside our recurrent neural network. We will use optimizer. As you can see, this is Adams. Adams is one of the best ones. Optimizer, which this optimizer represent what kind of gradient descent we will use. Adam is just one kind of gradient descent, which means that how we can uh, arrange our weights and biases. We will use Adam optimizer, or we can say Adam algorithm. And loss function we will use because this is a categorical problem, right? Because we will predict not a continuous value, we will predict just 1, 2, 0, 1, 2, 3, 4, 5, which represent every single emoji or labels of emojis, sadness, love, joy, something like that. And therefore we will use categorical cross entropy. If it was a 2 output, for example, from our previous one, we try to predict 2 output, 1 or 0. For example, if we predict a mail is a ham or spam, we will get a 1 output, right? This is a binary output. So for this kind of problem, we will use binary categorical entropy, binary cross entropy. But because the number of categories is higher than 2, and it's a categorization problem, we will use sparse sparse categorical cross entropy. Cross entropy. And for matrix, we will use accuracy. Yeah, when it goes from difference every time, we will see the result with the accuracy matrix. Yes. Let's see the summary of our model. Summary. We can use this method. Yes, this is the summary of our recurrent neural network. As you can see, it's a sequential model, which means that every neural network has been connected with each other is a sequence of line. Because it is a recurrent neural network, it should be a sequential model. So I think it's necessary. Because we will come every time and reassign our weights and biases, and also we will create the new outputs. So we have to come again. It's a sequence of line, and the output of the one of the networks will be the input of the next one. So we are using embedding. Embedding means as I said, there are embedding model, as I show you here, which represent number of the words we are using, 10,000. And we also created three bidirectional model. And also at last, we have created a dense layer, which normally represent the final output of our recurrent neural network, which will be a label of the emojis, okay, according to tweets. Yes, after this one, I think our model is ready to fit the data, right? It is simple for every algorithm inside every kind of machine learning. We will just fit, we are using after object of the algorithm, we are using fit function. Okay. What kind of data we will fit? We will fit for our training data, right? So we have to find our the actual not validation date. Yes, leave TV2. This represents the ready, the final ready our tweets. Okay. Yes. This is our axis because for our problems we are using, for example, in order to predict the house of the price, we use, for example, the size of the house, something like this. But for this problem, our axis, our inputs, is the tweets. Okay, we have just transformed these tweets into the numbers, which each number represents a single word. Okay, so we will also use the labels. This will be our y. Okay, because we will predict the labels for this recurrent neural network. Let's find the labels. Yes, labels too, I think, represent our labels. Let's find and write here. Yes, this is our y's. For fitting, we are writing here x, which is represented by tweets now here, and the labels represent our outputs. Okay. And after that, because we are using a validation data, okay, so we will also use validation data parameter, and inside this one, inside square brackets, we will write here our validation tweets and our validation labels, and every epoch it will compare the results of the training with the validation data, and give us the outputs, how accurate our model is doing, right? Validation labels too, I think. Validation labels too. This is our labels, and for validation tweet, validation tweet too. Okay. Our tweet is represented validation tweet, val tweet 2, and labels has been represented val label 2. Do you understand, right, Nikolai? There are no problem here. I'm just because it's not easy to memorize just every these variables. So okay, now this is our validation data, and yes, and after that we will create number of epochs. Okay, how many times it will go recurrently. We are saying maybe 20. Let's start with 20. If it's not enough, we can increase, or if it is high, we can decrease. But for example, we can write here whatever number we want. For example, let's say 1000. Okay, it's very hard job for the computer, but thanks TensorFlow, we had a callback, which means if the output of our training algorithm is very separated from the validation data, it will stop the training of the algorithm. Okay, so we can use callbacks parameter, which will enable us to stop the training when it becomes to separated from the original one. So we don't need to be, when we use callback parameter, we don't need to be worried about, okay, is my number of epoch is right or high or low. You don't need to worry about it. If maybe it is just two epochs, okay, and after, if it will begin to separate from the original or from the validation data set, and it will just stop training. It means that our model is outfitting, so it will stop training and return the output. Um, for for callbacks, we can use TensorFlow in order to assign from Keras. I can actually export this one separately, but we can also export inside the function. It's not from callbacks dot early stopping. We means that early stopping. It will stop early. It has some also some parameter inside the stuff. One of them is monitor parameter, which we assign what kind of arguments this early stopping will use. We will assign validation accuracy, because we say that if our training model predictions separate from the validation accuracy, and it will use this as monitoring for itself. Also, we will assign patience parameter, which we will say that how many times you will endure. For example, after it will diverge from the actual validation accuracy, how many times you will endure. For example, after 10 times you want to go continue your algorithm 10 times more, or 2 times, or 100 times is not feasible. Generally 10 or 2. I say 2 if it will diverge from the original validation data. If the our prediction will become worse and worse, after 2 times, 2 epochs, just stop it. Okay, it continues to, because I give a patience number 2. It means that keep going 2 times more, maybe it will be better, or if it continues to get worse after 2 times, 2 epochs more, and it will stop. Okay, this is the callback parameter, and we are just calling from TensorFlow callbacks early stopping function. Yes, I think is our model. If I didn't write TensorFlow, let's import. We have not import TensorFlow separately. Maybe this is the reason. Not callback. I think callbacks. Yes. Now, yes, our model is training. This is the first epoch, because if you remember from previous tutorial, normal artificial neural networks trains very fast, but the recurrent neural networks include a lot of complicated function mathematical operations. It will take more time. Do you see that we are now the first epoch, which means that we have not finished the first epoch here. You see the losses and the accuracy. The accuracy is increasing. Do you see that? Now this is the result of our first epoch. Now we are going to the second epoch. As you can see, this is the amazing result of the deep learning. After the first training, the accuracy has increased 80% from 39% to 81%. Do you see that? And the losses from 1.50 to 0.5, right? And it's going, yes, now we are increasing, the accuracy is increasing, as you see. the validation data we are assigned here is represented here because we use validation data, we also, this algorithm also compared the training results with the validation loss or validation accuracy. Not only training data set, but also validation data set, uh, which means that the results of the validation loss or validation accuracy almost similar to the results of the test data. Therefore, we use validation data. It is not using the tweets or labels from the validation data. It just compares the result. Okay, this is the difference. But when it comes to new tweets too or labels too, now our algorithm is using actually and making some changes, making its some changes in order to make the best predictions. But when it comes to validation data, it just only compare the results, nothing more. Do you see that? Now we are in the fifth epoch, and the losses has been decreased from the first epoch. It was 1,49, and now the losses, which means that uh, which we higher loss results, which if we come closer to the zero, it means that our accuracy is increasing, right? So this loss function means that the difference our predictions and between our predictions and the accurate values. So if the difference is high, which means that our accuracy is very low, and if the difference is very close to zero, which means that our accuracy is very high. Do you see the results? Or we have almost for the training data set 97%. If you use the accurate layers, deep learning also outperforms other any other kind of machine learning, normal machine learning algorithm. What kind of problem you deal with, no matter as a regression problem or categorization or for example translation or video recording, something like that, anything, it will outperform anything when we compare to the normal machine learning algorithms. So our accuracy has been increasing for every training. And as you can see, validation accuracy is also increasing, right? From 72%, it is coming to the almost 90%, which means that when we predict to do actual test tweets, when we take tweets that our algorithm has not trained with, it will predict almost 90%. Yes, it stopped. Even though I write here 1,000 epochs, it should we may think that if I didn't use callbacks here, it will train our model 1,000 times from the beginning to the end. Okay, this is the reason callbacks is mainly used because we don't know how many epochs we will use. We will train our algorithm. So therefore, callbacks is a very simple function. I'm normally just copying from my previous notebooks and pasting. You don't need to memorize it, but the one thing you should memorize, okay, I have a callback parameter which enables me to train when I train the algorithm to stop. I don't stop the algorithm if it separates the verge from the accuracy. Okay. Yes. Uh, so after the eighth epoch, it has been stopped, which means that we have give for early stopping two patients, two more epoch. I think after the sixth epoch, the algorithm understands that the losses is not going down enough and the accuracy is not going high, so there is no need to train the model more, and it just stops. Okay, so very good, very good. And let's evaluate our model. We use the same thing. Maybe you can history. That history will return the history of the training of our algorithm. Yes, we can see here separately, but also we can get the result inside by using this method. As you can see, our losses, our accuracies has been listed here, but this is not useful. Therefore, I will create a pandas data frame. Pandas data frame makes the visualization of the data inside tabular form, inside tables, right? So let's use pd.dataframe. Inside this function, I'm just pasting the previous code. And then, as you can see, it's very good. So we can easily see the results of the losses, accuracies, and validation loss and validation accuracy, right? It's very good to analyze the results. And I will copy this one by just adding dot plot, okay? Dot plot, which returns me a plot, a figure of these results. So these tabular form or tables will be represented inside a figure. By using just dot plot function is enough. I will just inside this one, I will increase the size of the figure. Big size enables me to do that. Let's run this code. As you can see, Nikolai, we will understand better now. The blue line represents the loss function of the training data. The red line represents the loss function, loss of the validation data, okay? And this orange line represents the accuracy. As you can see, 80% to it's going to almost 90%. And as you can see, after the training epoch peak, as I predicted, the accuracy is not increasing. Do you see that? It's getting worse, and therefore our callback stopped the training the model because it will not be better. This is the highest point that our training model can get to. Of course, we can make some adjustments, but according to this model I have created here, it will not get better, no matter how many epochs we train with. Okay, and then yes, as you can see, after this is the loss is getting closer from more than 1.2. It's going to the 0, which means that my accuracy is increasing. The difference between my prediction and the actual value is decreasing to 0. If it's a 0, and it means 100%, I can predict truly. But it's very close to the 0. If you can see, after the 6th epoch, these numbers represent the epochs of the training. It is not getting better, right? So therefore, it just stopped the training, our model. Yes. To this point, is there any question, Nikolai?
No, I don't think so. It looks very nice. It looks like it functions very good.
Yes. Actually, as I said before, you will encounter many coding for training recurrent neural networks, but they are very complicated. To understand and make it simplified for you is a very hard job. And actually, in order to create this notebook, I use a lot of time because it is very hard, difficult to find a relevant course or explanation. Some of them very hard code, and this discourage us to learn artificial neural networks, recurrent neural networks, and something like that. I believe also the same, a very simplified version. Of course, you can use the same model, for example, for predicting something similar. Okay, we predicted the emoji of the tweets according to the includes of the words inside the tweet. We now predicting that what kind of emoji will be according to this tweet. And according to the results, we have almost 90% accuracy for our validation data, but for training data, it is almost 100%, 97%. Very good result.